This is the third lecture of Introduction to Nuclear Engineering. We will deal with atomic energy and nuclear physics today. Now, radioactivity calculation. So, some of you learned during high school period about this, but normally, if you don't attend physics lecture 2, you are not familiar with this concept. So you have to learn some definition. Alpha and gamma and n in the first formula, and n means number density. How many how many elements? So there is number. N is number. Nt means number of element at time t. Nt means number of element at time t. Lambda means is actually this number. Actually, this is the probability of radioactive decay. So, for example, when we have 100 elements, uh, we, we don't expect all of the element decay at the same time. Some decays early, some decays late. So this is a probability. So lambda n means the number the port lambda means the number of uh, element the ratio of element that undergoes radioactive decay. So if we multiply lambda n and n, that means this amount of element uh, undergoes radioactive decay. So we define that alpha activity. So activity means decay constant times number density. So there is an activity. So that means initially we have nt number of elements, and among them lambda n undergoes decay. That means there is no the number of lambda n, the amount of lambda n disappeared because they undergo decay and they become a different element. So we call that activity. So alpha 0 means uh, activity at time 0. Activity at time 0. So let's think about this. In the balance equation, CF, balance equation. Uh, at time t, uh, the number disappeared number is lambda n. Okay, because it disappears, there is a minus sign. So minus d and t equals lambda n t. Okay, so when we convert this into dn dt equals minus lambda n. Okay, dn dt equals minus lambda n. We can rearrange that easily. dn dt equals minus lambda n. That means when we want to know the function n, dn dt equals minus lambda n means when we differentiate the function nt, then we get again nt and the minus lambda coefficient, right? That means nt is exponential function. So nt does not change. So and after differentiation, we have minus lambda n as lambda as a coefficient. That means in the minus lambda appears before t. So we get alpha 0. exponential minus lambda t. That is the form of activity. So the unit of radiation is firstly becquerel. Becquerel is 1 disintegration per second. So 1 decay per second is we call becquerel. So when we think about the Avogadro number, that is 6.02 times 10 to the 23. That means 1 becquerel is quite small number. 1 becquerel is quite small number. So we need a higher number units for the radiation. That is called 1 curie. 1 curie means 3.7 times 10 to the 10. DPS means 1 becquerel. So from the above equation for alpha, when we divide both sides with lambda, we can get nt equals n0 exponential minus lambda t, right? So that means initially n0, initially we have n0 element, but after time t, it decays and the exponential minus lambda t is lower than 1. That means it is reduced to n0 times exponential minus lambda t. The half-life is calculated like this. When the number of elements become half, so that is the half-life, 반감기. So from the first equation, when we put replace t, small t with t half, then we can get this kind of equation. So the alpha 0 becomes half alpha 0. So alpha 0 is cancelled in both sides. So the equation becomes this. And that means the t half-life equals 0.693 over lambda. So this is the equation for half-life. So this is quite important slide. So I will speak a few expression in Korean now. 액티비티는 붕괴상수 람다에다가 숫자 number density n을 곱해가지고 알파는 람다 n으로 정의가 됩니다. 그런데 요거는 뭐냐면 전체 nt 개수 중에서 어떤 시간에 붕괴되는 게 람다 nt 개수만큼 붕괴돼서 없어진다는 겁니다. 방사선을 내고 그 얘기는 뭐냐면 바로 오른쪽에 있는 식처럼 마이너스 dn 이거 뭐예요? 개수가 줄어드는 양은 람다 n 만큼이다 이거죠. dt라는 시간 동안에 줄어드는 양은 람다 n 만큼이다. 여기서 dt라는 걸 좌변으로 넘기고 마이너스를 우변으로 넘기면 dn dt는 마이너스 람다 nt 이렇게 나오겠죠. dn over dt는 마이너스 람다 n. 그러면 우리가 nt라는 걸 알아야 되는데 dn dt 한 것이 n을 한 번 미분한 시간에 대해서 한 번 미분한 것이 마이너스 람다에다가 nt 자기 자신이 다시 나왔잖아요. 그러니까 어떤 함수를 미분했는데 자기 자신이 다시 나온다는 거는 그 함수가 익스포넨셜 함수라는 거죠. 이거는 모르면은 따로 공부를 하셔야 됩니다. 이거 외우고 넘어갈 수가 없는 겁니다. 이건 수학을 좀 아셔야 되는 거니까. 어떤 함수를 한 번 미분했는데 자기 자신이 다시 나왔다. 그럼 그건 익스포넨셜 함수라는 거고 그 앞에 개수가 람다 마이너스 람다가 나왔다는 거는 t 앞에 마이너스 람다라는 개수가 있었다는 뜻이죠. 그러니까 t라는 거는 요 밑에 있는 식처럼 n0에다가 exponential 마이너스 람다 t 이렇게 된다는 겁니다. 그걸 풀면 그죠? 그게 이제 우리가 미분 방정식 푸는 거죠. 지금 여러분들 미분 방정식 배우고 있을 거예요. 자, 그래서 여기서 nt는 n0 exponential 마이너스 람다 t라는 게 나온 겁니다. 그렇죠? 거기다 양변에다가 알파를 곱하면 맨 위에 있는 식처럼 알파 t는 알파 제로 exponential 마이너스 람다 t가 되겠죠. 그 다음에 half-life, 반감기라는 거는 어떤 시간이 지나면은 원래 있었던 물질이 반으로 줄어드느냐 이겁니다. 그러니까 맨 위에 알파에 대한 식에서 스몰 t를 갖다가 half-life t 2분의 1로 바꿔줬을 때 원래 있었던 알파 제로만큼이었었던 게 절반, 2분의 알파 제로가 되는 시간을 찾아라 이거죠. 거꾸로. 그러면 위의 식에서 알, 어, 자, 알파 제로 알파 제로는 양변이 지워지고 익스포넨셜 람다 t 2분의 1은 2분의 1 이렇게 나오겠죠. 이걸 양변에 자연 로그 취해가지고 구하면 t half life는 자연 로그 2 나누기 람다 이렇게 나오겠죠. 요 식은 이제 꼭 아셔야 되는 식입니다. 이건 뭐 외워야 되는 식입니다. 오케이, next slide. When we have decay chain like this, A becomes B, and B decays into C, and C decays into D, then the equation become a little bit complex. So at this stage of your knowledge, you cannot derive this thing. You are learning engineering mathematics now, and in 1 month period or 4 weeks, in 4 weeks, you will learn how to get the solution from the above equation. dn dt equals r minus lambda n. But this is we call a decay chain interaction. So uh, this I will not forget this, and in 4 weeks I will ask you to derive this equation n equal n0 exponential lambda t. So at this stage you don't have a mathematical skill to calculate this derive the solution. So I will just skip these pages. Uh, Later on, this is the example using just previous uh, derivation. So you cannot, even though you cannot derive the formula, you can use the formula to get the solution. So at the end of this section, I will ask you to apply the formula to solve example 2.6. Okay? Now, this is nuclear reaction, 핵반응, nuclear reaction. Uh, this is kind of notation. A plus B becomes C plus D. A means projectile. B means target. So we 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 throw A to B, and then the product becomes C and D. And the large one is C, smaller one is D. This is kind of notation. So the left-hand side notation A plus B becomes C plus D. It has the same meaning with A parenthesis B, comma C parenthesis D. This is the same meaning. 어, B라는 타겟에 A라는 물질을 딱 때렸더니 C와 D라는 서로 다른 물질이 나오는 것을 우리가 핵반응이라고 합니다. 원소가 달라지는 거죠. 여기서 A를 프로젝타일, 던져지는 물건, B는 타겟, 맞는 물건, 그 다음에 C, D는 만들어지는 건데 만들어지는 것 중에서 큰 거를 C로 쓰고 작은 거를 D에다 씁니다. 이게 기본적인 핵반응을 나타내는 노테이션입니다. 그 핵반응이 뭔지는 몰라도 이런 식으로 씁니다. So this is the basic notation of nuclear reaction. So when we put an energy balance, the energy balance become like this. EA plus EB means kinetic energy of A and kinetic energy of B. MAC square and MBC square means rest energy of A and rest energy of B becomes the kinetic energy and kinetic energy of C and D and rest energy of C and D. So that means the energy should be conserved. 에너지가 보존돼야 된다는 뜻이죠. 반응 전과 후가. Now we can calculate the Q value of Q value. So in this calculation of Q value, we consider the rest energy only. So MA plus MB is the original rest energy, and MC plus MD is the the, the product rest energy multiplied by C square. So if Q is larger than 1, that means uh, the mass of A plus B is heavier than mass of C plus D, right? So if Q is plus, that we call exothermic, 발열 반응. So when Q is less than 0, we call it endothermic, 흡열 반응이라고 합니다. So this is the nuclear reaction. This is a basic principle of nuclear reaction, and it applies to nuclear fission as well. Now, example 2.7. Complete the following reaction. So, uh, nitrogen 14 and neutron. That means neutron is projectile and nitrogen 14 is target. And the product is hydrogen. And what will be the other project? So the number of nucleons should be preserved. So that means uh, new, in the left hand side there is the proton number is 7 and neutron number is 8 because 14 we have 7 proton and 7 neutron and plus n. So in the left hand side we have 7 proton and 8 neutron. In the right hand side we have 1 proton. That means the question, the unknown, we have 6 proton and how about neutron? Six neutron and eight neutron. So 6 proton and 8 neutron. That means carbon 14, right? So the number of neutrons should be preserved as well. Number of energy should be preserved, and number of nucleon should be preserved in the nuclear reaction. Now, this cover is very important. Binding energy. So when we have, for example, when we have iron, when we have iron, uh, there, for example, uranium, there are 92 proton and in total 238 neutron and proton inside of the nucleus of uranium 238. So that means we have 92 proton and 100 something neutron. So there is the formula, the first line, delta means mass defect, and the number of proton G times mass of proton plus N, number of neutron times mass of neutron, and actually material mass A. There actually it is not zero. There is certain number. We call that mass defect. This amount of mass, we believe, is used to bind nucleons. Okay. 어떤 물질이 몇 개의 양성자랑 몇 개의 중성자로 구성되어 있을 때 양성자의 개수에다가 양성자의 무게, 그 다음에 중성자의 개수, 그리고 중성자의 무게를 곱해가지고 그 실제로 그것이 결합되어 있는 어떤 물질의 무게를 빼보면 숫자가 꼭 남아. 그걸 갖다 우리가 mass defect, 질량 결손이라고 부르는데, 그 질량 결손된 부분이 결국은 그 핵자들을 흩어지지 않고 모아놓는데 바인딩하는 에너지로 그만큼이 쓰였다고 보는 거야. 그걸 갖다 우리가 바인딩 에너지라고도 부르고 질량으로 환산했을 때는 mass defect라고 부르는 거야. So this is the basic concept of binding energy and mass defect. So figure 2.8 shows binding energy per nucleon. Per nucleon means, for example, uranium-238 atomic mass number is somewhere here, 238. So about 8 MeV is binding energy per nucleon. So in total, we have multiplied 238 times 8 to get the whole binding energy of uranium-238. So this is binding energy per nucleon. 핵자당 binding energy. 그러니까 우라늄 238 같으면은 여기 요쯤 가면은 한 8쯤에 만나네. 그 핵자당 8매브만큼의 바인딩 에너지를 가지니까 238 전체에 대해서는 238 곱하기 8만큼의 그 바인딩 에너지가 필요했었던 거지. 이건 핵자당 8매브라는 거니까. So this curve shows the peak appears somewhere between 56. So 56 means iron. So the binding energy of iron is binding energy per nucleon of the iron is the largest. So the heavier element than iron, the binding energy is reduced, and lighter element than iron, the binding energy is again reduced. So binding energy of iron is the largest. So when some material becomes the size of iron, the binding energy is large and mass defect is large. Okay, so that means heavy nucleons like uranium-238 emits energy when it splits, and light element like tritium and helium, when it becomes the size of heavy material, that means when it undergoes a nuclear fusion, it emits energy because the binding energy of iron is the largest. So the heavier material emits energy when it becomes split and becomes the size of iron, and the lighter element emits energy when it fuses. 이 그림에서 보면 핵자당 바인딩 에너지가 56번 철이 제일 높습니다. 그러니까 어떤 물질이 56보다 큰 물질, 우라늄 238이나 235처럼 큰 물질은 이게 작아져 가지고 잘라져서 그 철에 가까운 사이즈로 줄 때 핵자당 에너지, 매스 디펙트가 커지는 겁니다. 그러니까 에너지가 많이 나오는 거고, 또 거꾸로 56보다 작은 물질은 뭐 트리튬이나 헬륨 같은 물질들은 합쳐져 가지고 더 큰 물질이 56에 가까운 물질이 될수록 매스 디펙트가 커집니다. 그러니까 핵 융합을 할 때 에너지가 나오는 겁니다. 그러니까 철보다 큰 물질은 핵 분열을 할 때, 철보다 낮은 물질은 핵 융합을 할 때 에너지를 나타내 준다는 것을 보여주는 그림입니다. So, example 2.9 is calculate the binding energy of last neutron in carbon 13. So, the the mass of carbon 12 is exactly 12 because we use that as a reference, and the mass of neutron is 1.00866. So that that is carbon 12 and one neutron, and the carbon 13 has the mass of 13.00335. That means the mass defect of these two is 0.00531. So actually, uh, the energy of one atomic mass unit is 931. You have to memorize this number. The rest mass energy of one atomic mass unit is 931. So when you multiply 931, we get 4.95. So 4.95 is the binding energy of last neutron. Okay, we can calculate like this. And this is magic number. Magic. Magic means we don't know why, but we don't know. But the no, element 2, 6, mass number 2, 6, 8, 14, 20, 28, 50, 82, 126. Mass number elements are quite stable. We don't know why. So that's why we call this number as a magic number. Just read 2, 6, 8, 14, 20, 28, 50, 82, 126. So, you don't have to memorize this one, but you have to be familiar with this number. So read this 3 or 4 times. Okay? This is magic number. We don't know why, but mass number 2, 6, 8, 14, 20, 28, 50, 82, 126 elements are quite stable. Now, nuclear model. So let's think about model. Uh, when when I was an elementary school student, I visited a science museum and saw a model for the glucose or model for sugar. So I wondered, this model is sweet or not. Actually, this is not sweet. This is just model. Okay, so model means it is not really that thing, but we uh, we make some image or we make some replica of the situation. So we understand how this look like when we probe into the thing. So it is like fashion model. Fashion model shows how it shapes when she wears certain clothes. So so this is a model, not real life, but we can understand how it behaves by the model. Okay, so the shell model is as we discussed before, there is orbit in the inside of the nucleus. There is nuclear orbit. So that is we call shell model. Sometimes we have used liquid drop model. So the nucleus is like liquid drop. So we will not go very far about these models. But you will learn this model from atomic physics. By the way, this is the equation for distribution. So uh, the most familiar distribution is normal distribution, 정규분포. So normal distribution means the uh, number of elements behaves normally. So from the mean, there is minus sigma plus sigma. So there is a distribution like this that we call a normal distribution. So when we get a product, it follows normal distribution. We don't know why, but normal distribution is well applied to manufacturing product. So there is a upper limit and lower limit. So there is a 95 confidence level. So you are quite acquainted with that kind of normal distribution. Now, in the gas dynamics, Maxwellian distribution is quite well applied to the number density. So we don't know why, but it just applied well. That's why we use this one. So let's look at this thing. Uh, NE means energy dependent number density. So number of element, atom or molecules, number of element with which have energy E is Ne. So it equals uh, I don't know why there is 2 pi, just 2 pi divided by pi kt E power of half exponential minus E per kt. That this is we call Maxwellian distribution. So when we have a Maxwellian distribution, we can calculate uh, most probable energy and average energy. So uh, most probable energy can be calculated like this. We differentiate above equation Ne with E and uh, find E that makes the differentiated equation equal 0. In that way, we can calculate the most probable energy. And when we if we would like to calculate average energy, we it is we know the averaging process. So average energy becomes we just multiplied E to the above distribution and just integrate it to get the average energy. So this is your first assignment. So calculate the most probable energy and average energy. And you already got the solution. And but you have to submit how you calculate the most probable energy and average energy. 어, 한국말로 하겠습니다. 우리 정규분포가 무슨 제품 생산할 때 정규분포 잘 따르죠. 사람 키 이런 것들도 잘 따르는데 왜 정규분포가 맞는지 몰라요. 근데 잘 맞는 거죠. 근데 가스, 리퀴드 이런 경우에서는 맥스웰 분포가 잘 맞습니다. 그래서 이걸 보시면 어떤 에너지를 가지는 아톰들의 개수는 N이죠. 그게 우변처럼 표현된다 이겁니다. 어, 이 그러면 이게 어떤 에너지를 가지는 게 몇 개다. 이걸 갖다 우변처럼 계산할 수 있다 이거죠. 그러면 most probable energy 가장 피크가 되는 거, 에너지 가장 개수가 많은 거, 그거 어떻게 구하겠어요? 그 위에 식을 갖다 미분해 가지고 0 나오는 에너지를 구하면 most probable 에너지가 되겠죠. 그죠? 위에 맥스웰 디스트리뷰션을 갖다가 에너지에 대해서 미분해가지고 0 만들어주는 에너지를 구하면 most probable 에너지가 되죠. 에버리지 에너지 구할 때는 위에 분포에다가 에너지를 곱해야죠. E에다가 위에 있는 분포를 곱해가지고 그거를 0부터 무한대까지 적분하면 2분의 3 KT라는 에버리지 에너지를 구할 수 있습니다. 요거 숙제로 제출하십시오. 어, 이게 숙제인데 이거 어, 일, 일주일? 한 일주일 시간 드리겠습니다. 제출하십시오. 예. 이메일로 제출하면 됩니다. So, as to the assignment, I will give you 1 week to submit. Just submit by email to me, okay? So, this is the gas law. PV equals nRT. We learned from high school level. And when we divide uh, uh, this expression, when you rearrange this equation and arrange with respect to p, that means we divide both sides with v. Then we can arrange like this. So k means Boltzmann constant, and n means number density. Okay, this one. N is number density. Number density. Density means number divided by volume, right? So look at the first equation. Uh, right hand side, road, use the expression of the second side. So the rho density means mass divided by volume, right? So when we put the expression for rho to the first equation, m will cancel out, m will cancelled. So that means this equation leaves v and a over v. So number of atom divided volume. So that we call number density. 다시 넘버 덴시티라는 것은 어떤 볼륨당 몇 개 있느냐 이걸 갖다 넘버 덴시티라고 부릅니다. 아톰 덴시티라고 부릅니다. 이거는 밀도의 정의를 생각해 보면 질량을 부피로 나눈 게 밀도니까 거기다가 또 질량으로 나누게 되면 MC 캔슬되고 NA 곱해지면은 개수 몇 개 나오는 거니까 아톰 덴시티라는 거는 어떤 볼륨에서 차지하고 있는 분자가 몇 개인지 그걸 갖다 볼륨으로 나눈 거죠. 그걸 아톰 덴시티라고 정의합니다. 앞으로 계속 이런 익스프레션을 사용하게 될 거기 때문에 이걸 외우셔야 됩니다. Now, when there are many elements in occupying the same volume, we can put an index to I. For example, 1, 2, 3, 4. We can calculate the same way the number density of certain element I like this. The same expression. And if we would like to consider the atomic abundancy, then we put atomic abundancy gamma and the percentage expression 100 divided by percentage expression, then we get the third line of equation, this one. Okay, as to this example, I will leave you to your homework. Just read and rewrite it and submit at the same time you submit the previous homework. Just write. I'm asking you, you just copy right because uh, if because when I ask that this, you will read this. This is the same. So this is same again. So as to this example, you will study and just rewrite it with your hand and submit at the same time as homework. Okay? Now let's call it a day. Bye.
수업 끝나고 오늘 교수님께서 말씀하신 과제 관련해서는 내일까지 이 캠퍼스에 자세하게 한 번 더 공지하겠습니다. 수업 끝났습니다. 수고하셨습니다.